Okay, welcome to a simple introduction to exponentials. So, first off, what is an exponent? That is probably the most important part. So, we all know, well, you should know, that an exponent is, well, it comes from when you take a square. Let's try making this as square as possible. We all know that this side has to be the same as that, alright? So if that side's the exact same, then why not make up a new term to say that? So we invented something called b squared, where you just take, let's say this side equals 3, and you say, okay, 3 squared equals this area, and that's a square of that number. So then they realize, well, what if you do that to other things? Like, let's make a 3D cube. And you're like, oh, well, let's just put that to the third power. And you can make 40 cubes and so forth with this, so then it becomes 3 to the third, and then that will give you the value. You can make it in 4 dimensions, and you can keep going. People start realizing there's more use to that. And that's that. And let's put that into an equation. Let's make x a variable, and then put it to some power, such as 2. Or we could do x to pretty much any other thing. So let's put that x to the... Yes? Okay, sorry about that. So what you have here, if you have your p, so it's up to your p, so this is a polynomial, anything bigger than a square. You also, well, anything bigger than a square is now considered a polynomial, even though you can cube it to the third power, and then fourth power is just considered a regular polynomial. So, now that we've done that, so let me just get out this eraser tool here. Where'd it go? There it is. It's a little laggy. Okay, so let's just erase all this. It's all nice. And let's get back out a pencil. So, what would something like let's say you needed to model, you have a car, you have a nice little car, and you have a car, and you bought it, but you want to know how much it's going to cost later on when when it's all dead and it's dying and had a few accidents and it's not good. It's almost on its last few wheels, and it's pretty much gone, and it's all busted up. So you model it like this. So you know that you're gonna get some money afterwards. So we're gonna make this S money. Let's say it equals. Oh well, we know that it's the original value of the car here. Let's do that in a nice little goldy color. So the original value, so V equals, it was originally 10,000. So you know that's the original value, and so what you know that it's going to depreciate. Let's say you went up to somebody, you looked it up on like Carfax or something, and you realize it was going to depreciate by 7% every year. So you now know that it's going to depreciate every year by 7%. Now you want years to be represented by your good old friend Mr. Time. We're going to represent by T here. And so you have your letter T for time. And okay, so now we have 3 variables here, and you want it all to be in one thing. So let's take our first thing. We know that we have $1,000. I think that should be, well, okay. So we have 1,000, and let's think about this. If it was 1 year, how would you want to know that it was what was the price after 1 year? So we know that T is just going to be 1, so we can just ignore it. So let's just ignore it for now, and let's add in this bit for the equation. this little bit here. So let's add in 7%. But we want to know the actual price of the car. So let's subtract that from 100, which will equal 0.93, because we're doing this in decimal form here. There we go. But, so we know that's going to equal that. So we'd multiply it by that normally. But we also know that you needed to multiply it by this. This needs to be multiplied every single year. So we need to multiply this. We need to multiply this right here times that, or every single by the number of times this is. So how do we do that? Well, we know that multiplying something by itself is just when you raise something to a higher power. So let's just add that in right there. And we can go ahead and just add it in a lovely little color. And we'll put it up to the t power. And let's finish this off with a nice little parentheses there. And now you got your nice little equation. We got money right there equals your original value, which we put to 1,000, even though your car is probably really bad if you got for $1,000. And then we know it depreciates, so we subtract this from 100%. And that equals your real value. And now you know that. So, though the original formula for this is actually, so your original formula for this whole thing is going to be A equals P parentheses I plus your rate. So, let's get rid of this whole thing. Now, we got your, so here's the normal formula. The normal formula is A equals, these are just the normal variables for principal. Let's do that as P. Parentheses. I, which will represent here, your interest. So this could be like putting something in a bank or just really anything. Plus or minus your rate. So for example, let's see, we could have, the previous example had, you know, the car, you minused it from the thing to display growth, well, your decline. So plus or minus your rate just means basically either you add 100 or you subtract 100. That's the difference, for the most part. And then you put this whole thing right here to the power of t, or time. So now that's the equation that you would normally use. Now let's say you want to just do something algebraically, just pure mathematical. So if you just want to do something pure with math, how would you do that? Well, the way I would do it is you don't need to have any of these things, because that's just for real-world examples, something more like economics people use. So first things first, we got to put this to a regular Cartesian coordinate graph. So we have to do y, and then it has to equal some value for your standard equation. We're just going to use a, because that seems like a nice little letter. And then we have to put this whole thing equal to something. And as you probably assume by now, it's going to have to equal your x value. Well, actually not your x, your b value here. So let's put this to, let's use this green color here. And that will represent it. Okay, so you now take your little b, and you raise it to your x power. and you minus it by your, let's use this for your h value. Hopefully you can see that, h. And that minuses your h. And you probably know this from your vertex form, and that's just your change in x. So it shifts your whole graph to the right if it's positive, or to the left if it's negative. So let's do negative and positive. That's the difference. And then for your k value, let's use this little pink color here. Plus, oops. Okay. And that will shift your graph up if it's positive, or down if it's negative. So that's that. And this right here can inverse the graph. It will invert it. It will also invert it if the B one is here. So if they both invert it, if this one can invert that way, then this one will re-invert it. So if these are both negative, they'll end up creating a positive graph. Now if only one's negative, then they'll equal an inverse graph. So these both inverse it. So that's the standard equation. Now what does this all look like on a Cartesian coordinate graph? Okay, well let's make our good old y-axis here. And we can make a x-axis. And here we go. So the standard equation is let's say we're doing it's a decay rate. So if this b value, b is equal to something not equal, if it is greater than or equal to, well, not equal, just greater than 1, then it will grow. But if b is not equal to 0 and is less than 1, well, not, I'm sorry, if it is, sorry, if this is less than 1, but it is greater than 0, it will decay. If it's negative, though, it will just invert the graph. So that is why it has to be greater than 0. So if it's a decimal point, it's less than 1. Now, let's just draw something. Let's say it's greater than 1 and it's positive. Let's just draw how it interacts, okay? So it starts off from it starts off just like a regular graph, and it will move up. Let's say our h value is 0, and our k value is also 0, so it doesn't shift it at all. And it tries approaching this value here, which is 0. Now, if you have a k value, the k value is going to be whatever the asymptote is. So you could say k is the asymptote. I probably spelled that wrong. Never mind. Sorry about that. Let's just write A, because that's a weird word to write. But you could draw your little dotted line across there, and that's where the asymptote is. Your h value would shift the whole graph that way. And that really is the basics of your